I'm Shahryar. I'm the all the financial systems, all the communication systems, even the power grid, they're tied to GPS. And in a GPS jamming incident, it would cost billions of dollars a day just in disruption. So jamming can be very, very dire. So at Notch, what we're doing is we're making a new kind of antenna. We're using metamaterials, and we are activating them, and we in software, and so we can protect against jamming, and we can also beamform and boost range. So the core of our technology is this metamaterial. It acts like a transparent piece of glass, letting radio frequencies to pass through it when it's off, and when it's on, it reflects the radio frequency. So if you take a regular omnidirectional antenna that's radiating omnidirectionally, and you put a bunch of panels around it, now you've converted a regular antenna into a smart one. And let's go back to our example of our GPS jamming attack. So we have a GPS satellite, and it's receiving the Notch-powered GPS antenna is receiving the satellite signal, but our jammer comes in from the bottom left. And in software, we can activate each and every panel to bring down the spurious signal, and we can figure out that these set of panels should be activated, effectively reflecting the GPS jammer. We can also protect against multiple jamming signals. Now, if you're using this antenna as a transmitting antenna as well, and you activate the same set of panels, you can reflect, the RF energy can reflect on the inside, concentrate the power in one particular direction, boosting the range in that direction. And because it's controlled in software, you can activate other set of panels, and you can get it to beamform and steer in any particular direction. If you combine both of them together, you get secure links. So a bunch of Notch panels together can be used to protect against enemy attacks, enemy jamming attacks, can boost range and reduce RF fingerprint between communication between both of the antennas. Now, this was a demo we made before the xTechSearch. So we have a Notch panel, and in front of it is a horn antenna connected to a software-defined radio. And there's a computer right there, and we're going to turn on a jamming code that's going to go through the horn antenna, through the Notch panel, and jam the black computer's Wi-Fi card. So right now, we have a good signal, and we're going to turn on the jammer on the silver computer. Now the jamming signal is going to go through the Notch panel, jam the Wi-Fi card of the black computer, and when we power it up, so the panel can be powered, and then it'll reflect the jamming signal. So right now the bandwidth stopped, and you can see it was jammed, and it's now resuming. This was before we got into xTechSearch. This was the panel was tuned at 5.7 gigahertz Wi-Fi. So for our Capstone, what did we do? We made a tunable panel, and I'll go into what this is. Basically, we wanted to make it dual use. It go between GPS and Wi-Fi and any frequency in between. We also wanted to make it software defined, so no longer pushing power buttons on power supplies. And a stretch goal was to do autonomous jamming detection. So that was the stretch goal. So what is a notch tunable panel? So imagine you have a band of frequencies that you can now, instead of one frequency, like the previous case, 5.7, you have a band of frequencies, and from low frequencies to high frequencies, and you can get it to tune to any of those frequencies. And I like to use light as an example because we can't see RF. So imagine it's from red to violet, and you can tune it to, let's say, orange in this case. So it will let the orange frequency in when it's off, and when you turn it on, it reflects the orange frequency. Now, why is this important if you have a tunable surface? So if you have a software-defined radio and you're using for communication links, and you're doing frequency hopping, you can get the panel to hop along with that frequency. So we've built the notch tunable panel. It's 7 by 7 inches. It weighs 112 grams at the moment. It uses no power, and it tunes between 1.5 to 2.4 gigahertz. So our first demo is the panel and its performance. So we have two horn antennas. The horn antenna on the left, the horn antenna number 1, sends a broadband frequency range, broadband energy and frequency, and it gets received by the horn antenna number 2. And the amount it receives relative to the first antenna gives you its performance. So if you put a reflecting screen in front of it, you're going to get nothing. But if you make an aperture, a hole in it, you're going to get frequency through it. And then you put the panel, and you can see the frequency response of the panel. And that's all measured with the network analyzer, and we have a power supply. So that's that demo. And I'd like to invite the judges to come up and see how it switches, and also see the power it consumes. So right now, it's got no power, it's off. It's at 1.5 gigahertz. That's approximately GPS 1.575. And I'm going to turn it on to 5 volts, and that went to, that's Wi-Fi. So, and if I tune it, I can tune it and make it move.
So how much frequency resolution do you have in your tuning? So you have about a gigahertz of dynamic range?
Yeah, because 1.5 to 2.4.
Right, so how much resolution do you have at each frequency? Or, I mean, it seems it's broadband, but it's centered at...
Yes, it's centered.
So what's the full width half maps of that region?
Well, the bandwidth's 250.
Okay.
I guess the resolution would depend on the voltage, how fine you could get. I've not played around with how,
So it's dependent upon the voltage control,
right.
How much,
right.
I guess the preciseness of your
That's
voltage.
Right. So your A to D, if you're using an A to D converter. But I would like you to see the power usage. So if you look up here on the top right, that tells you how much power it consumes. And that should say 0. Power through that panel. So the panel's right here. Yeah.
So you switch the panel on, or it's off?
It's on, but it consumes no power, or I can't measure it.
So it's a voltage bias?
Yeah, it's voltage controlled.
And if you switch it off, it would turn back to
It'll,
the off state?
yeah, it'll go to 1.5. So by default, it's 1.5, and when you go to 5 volts, it's 2.4, and you can tune in between. And so on and off can be anything you want it to be in that range. Sorry, let me turn it on.
So in your mock-up, you essentially show a geodesic dome as
Right.
your mock-up. Is that how you envision the antenna shielding, or is there another geometric arrangement that you're considering for for this screen?
Yeah, so this is right now rigid. the panel's rigid, but we want to make it flexible so it can conform to an enclosure. So then it could be any form factor.
And the size of it, is that related to the frequency it'll?
No.
So
So I just made 7 by 7 arbitrarily. Yeah, I mean, you're right. There is a size, but size, like, I mean, scales with frequency, but it depends on the frequency you're using. But there's no reason why this was 7. Yeah.
How far away from the source or the emitter do you need the material to be? Is
That's
there
a
a
good
minimum
question.
distance?
Yeah, well, not for the panel, because the panel is sub-wavelength, so it can be close. It's more the antenna that has to be on the far field. And feel free to move if you want to tune it yourself. So you have to push it, and then. I think you went too high.
So it goes past 7, it doesn't do it.
Yeah, it didn't. Yeah. It was only designed for up to 5. Yeah. But I've not played around pushing it harder.
I don't want to break it.
Sorry, you have to press it. Yeah. Yeah.
Okay, so this is just moving in.
Yeah, voltage.
But in full volts, what about, can you tune it at tenths of a volt or hundredths
Yeah,
of a
yeah.
volt,
So you
or-
have to press,
Okay.
and then you can. And this is what the baseline was without that. So.
So what would be your, the actual implementation when you do that, this experimentation project?
Yeah. So.
Has some of the
Judges,
stuff here with configuration?
can I ask you to use this mic so we can hear? Hey, go ahead.
Sorry. I was just asking, in a fielded type configuration, what would this look like?
Yeah, so this would be around an antenna, so not just this panel, but multiple panels or multiple sections of panels that we could activate and then steer and block. And that's that demo.
So what do you see are the limitations of this?
Limitations, I guess, knowing beforehand the frequency, if the enemy were to know what frequency it was at, and then I don't think, there's a new way of doing it. It's,
You mentioned frequency hopping
Yes,
in your
right.
presentation. How fast does it cycle?
yeah, so
Milliseconds or?
the switching time is microseconds. Someone told me that I could get it to nanoseconds. I haven't tested that. So yeah, microseconds, at least the material. Then when it comes to the software and the computing, that might take more time.
And is it labor intensive to make your panel? Is it grown
No.
or is it manufactured?
Manufactured.
by
Manufactured
mechanical
by,
process?
yeah, mature process. So not expensive.
So piggybacking on her question, in terms of implementation, you would envision like a feedback controller controlling the panels almost in real time.
Right. And
adjusting.
I have some code that shows that.
Okay.
So,
You said you have a second demo?
yeah,
or-
yeah.
Okay.
So the ultimate goal is actually make this software-defined antenna, one that has computation in it that can activate the panels to protect against jamming autonomously, and also, if it's used in a transmitting case, to boost range. But this soccer ball is it's a truncated ICOS header, has 32 faces, difficult to build at the moment. So we went with a simpler design, a cube without a top and a bottom. That's that. So 4 sides, 4 faces, made of the same material. The 4 faces are numbered, so you have the big numbers, 1, 2, 3, 4. There are lights that turn on. That means that they reflect at 2.4 gigahertz. So the same panel can be used for GPS, but we use 2.4 Wi-Fi for this. And so our second demo is our using that box. So we have a hack RF software-defined radio connected to an antenna that's going to jam panel 1. So you can see Brianna is going to stand in front of the jamming antenna. It's very sensitive. If you can just, no, it's very sensitive. Like it kind of movement of people reflect the waves and just kind of gets all messed up. But okay, so we are in. So there's a computer in there, a small $35 Raspberry Pi off the shelf, and it controls the panels. And what we're going to do is we're going to turn it on. It's going to be transparent at 2.4. Then we're going to jam it. And you'll see the signal drop. And then we're going to turn on the panel 1 to reflect the jammer. And you'll see that the signal goes back up. So we wrote code now. We can activate any of the panels in code. And so that's our bandwidth. So it's connected to this server here. So they're transferring data between the server and the client. So this is the server, this little one, and that's the client. And now Brianna is going to turn on the jammer. Okay, so the bandwidth dropped. Can you turn it on again? Turn it off and on again. Can you increase the gain? $40. Okay. Okay. I think that should be good. Okay, so it's jammed now, and Brianna will turn on panel 1, and hopefully it will unjam itself. Seems like it's still jamming. Maybe we'll come back to this again because we have another video demo of it, but we'll come back to that. Okay. Can you do it again? Try. All right. Okay, so. Where were we? Okay, so while Brianna gets that working again, it was working 30 minutes ago, and we did do some code. We wrote some code on autonomous jamming detection. It's not a robust code yet, but it does demonstrate the concept. Same box. We have 4 faces, the jamming antenna in front of panel 1, and that's how it looks. So we have the jamming antenna here, panel 1. Panels 3 and 4 can be viewed in the mirror, and panel 2 is in the back. And so what we're going to do is the bit rate is measured on the left TV screen, and then the jammer can be activated, and you'll see it on the right. So let me press play. Yeah. So the bit rate is going. It's fine. It's at 30,000 kilobits per second. And now we're going to turn on the jammer. And it detected that it got jammed. And now it's going to start searching by activating each of the panels and figuring out how to block what set of panels, what to keep on to block the jamming signal.
So does the antenna need to be orthogonal to the panel, or what happens if the antenna is centrally decaying?
Yeah, so we've seen it turns on multiple panels. So 1 and 2, or the next video I have shows 2 jammers. So that kind of replicates your case where it's in the diagonal. But surprisingly, the code is actually quite hard. It's not as simple as I thought it would be, just a binary search. It kind of like throws off it knocks out the antenna from the network sometimes. So trying to get it so that it doesn't knock itself out is actually difficult. So was this fine? Do you want to go over it again? We have another one as well. So what if you had 2 jammers? One in front of panel 1, one in front of panel 4. And that's this demo. So we have panel 1, the jammer is right here, and panel 4, the jammer is right here. And we can see how it does it. So it's going to turn on. So that's our bit rate. It's measured fine. Now it's going to turn the panels off, and we're going to turn on the jammers. So it's detected it's jammed. Now, this algorithm was actually more complicated because if you turn on one panel, you're still being jammed from the other side, so how do you figure out how to keep those panels, or what sets of panels to keep on. So we measured differences, like before the rate at which when you turn on the panel and turn it off, and then it starts to figure out which sets of panels to keep on. So it's still searching panel 3, panel 4, and then you'll see it'll conclude to a set of panels. So panel 1. And now you can see the bit rate go back up. And it's still searching, but it'll finally conclude with three sets of panels. So 1, 4, and 3 were determined to turn on, and it resumed the same bit rate. And I'm showing you how that panel's off and that panel's on, the panel not in view. So, works? Okay, so we can try it again. How much time we have? 18. And then we'll get back to the conclusion. All right. So all panels are transparent right now, and Brianna's going to turn on the jammer. So its bit rate's gone down, and now she's going to turn on the panel 1. There it is. It's very sensitive. That's what we've seen. Moving around it, it'll go crazy sometimes. But yeah, so that's us working. Can you see panel 1 light up? Yeah. Thanks.
So it's sensitive in its on state, or it's also sensitive when it's off?
It's kind of leaky because it doesn't have a top and a bottom, and so it's sensitive. Like we've just seen it. We've not done simulations in a room to figure out how it looks, what the wave modes are like in the room. So all we see is like we move around and suddenly it'll just dip and then go back up. And so it's not. We believe actually it's a software. It's code. We have to make the code robust. That's what we believe. Okay, back to this. Let's see. So that it would be easily conformed to any enclosure that would go into any antenna system. And this is our team. And yeah, we very grateful for this opportunity. I want to thank everyone who organized this xTechSearch. It's been a great experience. So that's all I have. Do you have any questions?
So is it an assumption that you have to have a plane wave as you're coming in order for it to be blocked, in order to turn it on and block that?
Yeah, I've only thought of it as a plane wave. I've not thought of like, any birefringence or, any where the electric field is also in the direction of propagation. But yeah, I've thought I've only assumed it right now as a plane wave or no near field stuff.
So I guess in your demos, have you attempted any beam steering or beam forming in this?
Not in this. I took it out actually because I thought it would be confusing. I did have our first demo was a system that kept switching, but it was like a dumb system because it just kept switching. It had no autonomy to it. And we saw signal strength go up every time it switched in different directions. Yeah, we have a video of that, of a prior demo.
Okay.
But it used the 5.7 gigahertz material.
So what would be your next steps for maturing
Yeah,
the
so,
technology?
yeah, sorry. To make it flexible, to make it conformal, so it's now not rigid, so you can bend and you can stick it on things, and then develop the code. Yeah, and not use like off the shelf. We'd probably make a custom, chip that would sit in there, probably all on one, flexible material, and then activate it.
How long do you think it would take for you to get to that point where you are able to take this and make it bend and flexible? And how long do you think it would take you also to work on increasing the frequency?
Increasing the frequency?
Oh, you said it's at 5 megahertz right now.
No, it's right now it's 2.4 gigahertz, and we only picked that because Wi-Fi, The flexible part is not, I don't believe that would be difficult because it's, again, mature technologies. It exists in our phone and a lot of flexible substrates. So the trick with flexible is that it might, because it bends towards each other, it might detune a little bit, and that might be interesting, but I'm not so worried about it. It's the same process of making that, just flexible. And then the frequency, I think usually everyone wants to go lower in frequency. They want to go to VHF and UHF. So the manufacturing techniques are very mature for those. Not a problem. It's when you go higher in the frequency that you start to get manufacturing problems. Did I answer your questions?
Judges, any more questions? All right. Thank you very much for the presentation.
Thank you.
That's the end.
Thanks.